Yes, thank you very much for the introduction. And I want to thank the organizers for inviting me to speak here today. I'm very happy to have a seminar here. Yes, and I'll speak about a result that's a result in my PhD thesis, but it's joint work with Julie Desjardins, who is in Toronto. Yeah, so I wanted to mention that. Yes, so let's start. The setting that we're in is we have a variety over a field and we want to study its set of k rational points, x of k. And of course, questions that are often asked about the set, is it empty? Is it finite, infinite? And if it's infinite, is it then dense with respect to the Zariski topology? The latter is what I will focus on, density of the rational points. And of course, like we want to study these questions and answer them using the geometry of our variety. We have, of course, famously the example that for a curve of genus at least 2, we know that the set is finite. So the geometry really determines in this case that we have only a finite number of rational points. And this we want to study today for the Pezzo surfaces. Yeah, the surfaces that I will study always have already a rational point. So the first question is not relevant, but the density is what we'll focus on. Okay, I want to start by an example of the Pezzo surfaces, cubic surfaces in P3. So they form a famous class of the Pezzo surfaces, the smooth cubic surfaces in P3. Here's an example, the Kleb surface. There's many of these clay models everywhere around. It's a very classically studied object. And we know a lot about the geometry of these cubic surfaces. Already in the 19th century, Cayley and Salmon showed that such a smooth cubic surface over an algebraically closed field contains exactly 27 lines, and any point on the surface is contained in at most 3 of those lines. And here you see the picture a bit zoomed in, and you see all those lines very nicely. You see how they intersect. So this is very classical, classical stuff. And we know more than just that there's at most 3 lines intersecting. We know completely how they intersect. The intersection graph of these lines is the complement of this Schläfli graph. Okay, so the geometry on cubic surfaces is very well understood. What about their rational points? Also there we know quite a lot if you talk about density. So the following statements are equivalent. This is proved consecutively by Segre, Manin, and Collard. If a smooth cubic surface contains a k rational point, then there is a map from some projective space such that the image is dense in X. The second property is the definition of unirationality. So this means that X is unirational. And if k is infinite, this implies that the set of rational points is dense in X. So for cubic surfaces, we know that as soon as your field is infinite and you have a k rational point, then the set of rational points is dense in X, following from unirationality. Okay, so this was the geometry and the rational points on cubic surfaces that I wanted to show as an example, and we're trying to generalize this to Del Pezzo surfaces. So what are Del Pezzo surfaces? A Del Pezzo surface is a nice surface which is smooth, projective, and geometrically integral with an ample anticanonical divisor, which means that there's some embedding in some projective space of our surface, and under this embedding, some multiple of the anticanonical divisor is linearly equivalent to a hyperplane section. So this is very nice. We can always embed them in projective space, and the degree of a Del Pezzo surface is the self-intersection of this anticanonical divisor. This degree is always an integer between 1 and 9. And here are some examples. So the degree 3 Del Pezzo surfaces are these smooth cubic surfaces. Degree 4 Del Pezzo surfaces are complete intersections of 2 quadrics in P4. The Del Pezzo surfaces of degree 2 are double covers of the plane that are ramified over a smooth chordic curve. And Del Pezzo surfaces of degree 1, I'll go into detail later. In general, if the degree is between 3 and 9, then a Del Pezzo surface is just a surface of degree D in PD. And that is how Del Pezzo originally studied them. So degrees 1 and 2 are kind of a generalization of this phenomenon. Okay, so let's look at this geometry of Del Pezzo surface. I showed you that for the cubic surfaces, we know it very well, and this is completely the same for Del Pezzo surfaces of other degrees. So over an algebraically closed field, a Del Pezzo surface is equivalent to, birationally equivalent to the projective plane in the following way. It is the blow up, if you have a Del Pezzo surface of degree d, then it is the blow up in 9 minus d points in general position. In general position is no 3 points on a line, no 6 points on a conic, and no 8 points on the cubics, which is singular at one of them. So these smooth cubic surfaces are blow-ups of 6 points in the projective plane. I showed before that the smooth cubic surface always has 27 lines, and this we can generalize also to Del Pezzo surfaces coming from this blow-up description. So if we have a Del Pezzo surface over an algebraically closed field and it's constructed by blowing up R points in the plane, then there is always a finite number of lines. So this depends on the degree. And they are given by, of course, the exceptional curves that you blow up above the points that you blow up, but also this whole list of strict transforms coming from curves in the plane. So everything, all your exceptional curves or lines are determined in terms of the points that you blow up. And in this way, we can easily count the lines or exceptional curves on the Del Pezzo surface, and we can see how they intersect. For example, for degree 7, we blow up 2 points, so we get 2 exceptional curves. And of course, there's a line through those 2 points, and that will give us a third exceptional curve, and they intersect like this. Degree 6, we blow up 3 points. So we get 3 exceptional curves, and of course, between all of these 2 points, there is a line. So we get 3 more exceptional curves. And degree 5, we blow up 4 points, and we have all the lines of the pairwise intersecting between any of the 2 points, etc., etc. We can continue like this, and we can count all the lines on a Del Pezzo surface. Here you see the 27 lines on the cubic surface, and you also see that this grows very rapidly towards the lower degrees. And the degree 1 Del Pezzo surfaces really are a bit of an exception because there's so many lines that this is not such an easy configuration to draw. This is shown in the following. So we know the intersection graphs of these lines for several degrees. So for Del Pezzo surface of degree 5, we had these 10 lines and they form the Peterson graph, which is a known graph. The 16 lines on the Del Pezzo surface of degree 4 form the Clebsch graph. And the 27 lines, as I showed before, form the complement of the Schläfli graph. And for Del Pezzo surface of degree 2, we can still kind of reason this, what this graph should look like. So we have 56 lines, and now I say lines in quotation marks because they are not really lines under the embedding, they're exceptional curves. And any of these lines intersects exactly one other line with multiplicity 2 and 27 other lines with multiplicity 1. But these other 27 do not intersect its partner, so this is intersection multiplicity 0, and they form again the complement of the Schläfli graph. So the graph is still quite nice to describe, and from this we can also see that on the Del Pezzo surface of degree 2, there are at most 4 lines that go through one point. Because of these 27, which correspond to the lines on a cubic surface, we know that there were at most 3 lines going through a point, and we have 1 extra line intersecting them all. But for Del Pezzo surface of degree 1, this is actually not so trivial to just see from the graph. And this is another result in my PhD thesis together with my supervisor, that on a Del Pezzo surface of degree 1, a point is contained in at most 10 lines if the characteristic of the field is not 2 and 3, and at most 16 lines in characteristic 2 and 12 in characteristic 3. So we see that with the same reasoning with this graph, we actually got a number of 16 lines that could pairwise intersect, but this number drops to 10 in almost all characteristics. So this already shows that the degree 1 Del Pezzo surfaces are a bit more intricate and a bit more difficult than the other Del Pezzo surfaces, and this we'll also see in in studying their rational points. So what about the rational points on the Pezzo surfaces? So as I said before, a variety is unirational if there's a map from some projective space such that the image is dense. And I also said a smooth cubic surface has a k-rational points if and only if it's a unirational. This was this work by Segre, Manen, and Collard. And this result is extended to all Del Pezzo surfaces of degree at least 3. So this is again the consecutive work by Segre, Manning, Collard, and Piropan that for any Del Pezzo surface of degree at least 3 over a field K that has a k-rational point is unirational. So as soon as you have one rational point, you're unirational. And the degree 2 case is almost finished. There's one condition there. So as I said before, the Del Pezzo surface of degree 2 is a double cover of the plane, which is ramified over a smooth chordic curve. And Salgado, Testa, and Varilli Alvarado showed that the Del Pezzo surface of degree 2 over a field K, which contains a point outside this ramification locus of this double cover, and not contained in the intersection of 4 lines, is unirational over K. So this intersection of 4 lines, that's also the maximal number of lines that can intersect, and there's not so many points that satisfy this, but it also has to lie outside the ramification locus. And from this we conclude that, from this and the previous theorem I showed, that for any Del Pezzo surface of degree at least 2 over an infinite field that contains, as soon as it contains a rational point, with this extra condition for degree 2, then the set of k rational points is dense. Since universality implies density. Oh, there's some echo. Okay. Yeah, so for all Del Pezzo surfaces of degree at least 2, we know that as soon as they contain a rational point and they satisfy the condition in the case of DS2, then they're unirational, and if the field is infinite, this implies that the set of rational points is dense. Okay, and this brings us to the Del Pezzo surfaces of degree 1. So what about the density of rational points, or the unirationality of Del Pezzo surfaces of degree 1? Well, first we can restrict to the surface being k minimal. If the surface is not k minimal, which means that there is a Galois orbit of pairwise disjoint exceptional curves, you can blow down this whole orbit, and you get another Del Pezzo surface of higher degree. So we can use the previous theorems to determine if the set of rational points on the Del Pezzo surface of higher degree, x prime, is dense in x prime. But since x and x prime are birationally equivalent, the density of xk follows from the density of x prime k. So if x is not k minimal, we can just use the previous theorems to check for density of rational points or for unirationality. The minimal Del Pezzo surfaces are those with Picard rank 1 or 2. And there's one result on unirationality by Collard and Mella from 2017 that says a Del Pezzo surface of degree 1 over a field with characteristic unequal to 2 that admits a conic bundle structure is unirational. And those with conic bundle structure, it's the same classification as those with Picard rank 2. So the Del Pezzo surface of degree 1 that are minimal have Picard rank 1 and 2, and those with Picard rank 2, we know that they're unirational if the field has characteristic unequal to 2. But this is a very recent result, and apart from this theorem, the question is wide open. So we don't have any example of a minimal Del Pezzo surface of degree 1 with Picard rank 1 for which we know it's unirational, or for which we can show it, or an example of a Del Pezzo surface of degree 1 with Picard rank 1 for which we can show that it's not unirational. So this is really a wide open question. So let's go to something that's a bit more within reach to prove, something that's a bit less wide open. So as I said before, if your field is infinite, then unirationality implies the density of rational points. So a natural question would be, okay, if I have a Del Pezzo surface of degree 1, is the set of rational points then dense in X with respect to zero-sky topology? So we skip unirationality and we just want to know density. And for this, we expect the answer to be yes. So there's several partial results that I listed here, but there's also conjectures that point towards this. So in general, we expect that we should be able to prove this for all Delphi surfaces of degree 1. And today I'll talk about a bit about these results, and in particular about the results together with, this is Desjardins, Julie Desjardins, and myself. Okay, so to summarize the rational points situation that I talked about the Pezzo surfaces, if you have a Pezzo surface of degree D, and we assume it has a point, a rational point, then if the degree is at least 3, then the surface is unirational, and therefore also the rational points are dense because we assumed K to be infinite. If the degree is 2, then it's unirational if P lies outside this closed subset, so the ramification curve, and not contained in 4 lines. And this implies in that case also the Zariski density. And for the degree 1 case, we know that it's unirational if the Picard rank is 2 and the characteristic of the field is not 2. But Zariski density we know for several families. So that is, here we know a bit more about the density. And in the rest of this talk, I'll explain the strategy in proving these partial results that I said before, and I'll show the new result, which is joined with Julie. Okay, so now I'm going to talk about the density of the rational points on the Delpezzo surface of degree 1. I first want to say a bit more about their geometry. So a Delpezzo surface of degree 1 over a field K is isomorphic to a smooth sextic in the weighted projective space with weights 2, 3, 1, 1. So X has weight 2 and Y has weight 3, and Z and W have weight 1. And it's given by a homogeneous equation of degree 6. And from this equation, you see already that such a surface always contains a K rational point. So if I set X and Y to 1 and Z and W to 0, I have a point on this surface. So this is already nice. We already have a K rational point, but we have a map from X to P1 projecting on Z and W. And this is defined everywhere except in this point. So in a way, we have a rational point, but it's also a bit of an annoying point because it makes this map birational and not everywhere well defined. But of course, we can blow up this point, and then we obtain an elliptic surface above my Delpezzo surface. So I blow up the Delpezzo surface in a point, and I get this elliptic surface which is a surface where almost, with a morphism to P1, where almost all fibers are elliptic curves. And we have here already one section on the surface given by the point that I blew up, which is now an exceptional curve. So as an example, if I have the Delpezzo surface given by this homogeneous equation of degree 6 in this weighted projective space, then we blow up this annoying point and we obtain the elliptic surface. And the fiber above a point is exactly the fiber you would think it is. It is given by this equation, and this is isomorphic to an elliptic curve for almost all points in P1. So to summarize, for a Delpezzo surface of degree 1, I have this smooth sextic, and it has this point which I can blow up to obtain an elliptic surface. And this is what we'll use to prove the density of rational points. Because of course, if the set of rational points on this elliptic surface is dense, then the set of rational points on my Delpezzo surface is dense, because one is just a blow up of the other. And therefore, our goal is to prove the density of this elliptic surface. And this is, of course, very nice because you have the structure of a fibration, you have elliptic curves to work with. So yeah, you have a lot of structure there that is nice to work with. So how did people show so far the density of this set of rational points in my elliptic surface? Well, there's kind of 2 techniques in the literature. One is by studying the root number. So this is a result by Varilli Alvarado from 2011. And he studied these Delpezzo surfaces, diagonal Delpezzo surface. And under a condition that the Tate-Rayfish group of elliptic curves with J invariant 0 is finite, he shows that the rational points, the Q rational points, are dense in the surface. And he did this by studying the root numbers of the fibers, and he showed that there's infinitely many disjoint pairs of fibers with opposite root number. And of course, this means that there's infinitely many fibers with root number -1, so infinitely many fibers for which the rank is positive, because we assume this that the Tate-Rayfish group is finite, so then the parity conjecture holds, and yeah, root number -1 implies positive rank. So this is the root number approach. Another approach is by creating a multi-section. So if you have this elliptic surface again, this is a section which a curve which intersects every fiber exactly once. But you also have curves that intersect every fiber multiple times, for example, twice here, and those are called multi-section. And by creating these kind of multi-sections and showing that there's infinitely many copies of them in your surface, people showed that the rational points on this elliptic surface were dense. And this is the technique used by Ulas, Dogbeh, and Jabara in a series of papers, and by Van Lyck and Salgado. They have results for various families of Del Pezzo surfaces, and they show this by creating these multi-sections of low genus so that they can have infinitely many rational points. But very often they have to assume that this multi-section has infinitely many rational points. So that is sometimes a big assumption. We don't know if that's also necessary. Yeah, but that is the multi-section approach. And a recent result by me and Julie is we studied the surfaces of this form. So a Del Pezzo surface of degree 1 over an infinite field of characteristic 0 of this form, where A and C are non-zero. So in particular, B could be 0, and then we recover the surfaces that Varelli Alvarado studied, for example. And if you let E be the elliptic surface obtained by blowing up this point, then our theorem says that if X contains a point, a rational point with Z and W coordinates non-zero, and the corresponding point on the elliptic surface lies on a smooth fiber and is non-torsion on that fiber, then the set of rational points is dense in X. And the nice thing is that if K is finitely generated over Q, the converse holds as well. So then this condition is sufficient and necessary. So here's a picture that shows what I just said. So this is this point that I blow up to get this elliptic surface with the section. And the requirement is we have one other rational point that lies on a smooth fiber here and has infinite order. And this fiber is not above 0, 0, or Z and W are both non-zero. And this is the first result that gives sufficient and necessary conditions for this family, where over any field that's finitely generated over Q. So that is really nice about it. And yeah, the rest of this time I want to show you how we prove this theorem, because there's some techniques that could be generalized to other surfaces, and it's quite a nice proof. So we take X, Del Pezzo surface of degree 1, K, an infinite field of characteristic 0, and epsilon, the elliptic surface that lies above X. And we assume that X has this point P as in the theorem. So for any R in the elliptic surface with non-zero Z and W coordinates, we construct a 3-section of the elliptic surface, given by this very explicit equation. So this is an equation, it's the pullback on the elliptic surface of the Del Pezzo surface intersected with this hyperplane. And how did we get this very explicit equation? Well, we actually looked for this in linear systems on X. And the idea is that the linear system minus nkx has dimension given by 1/2 n times n plus 1. And a general curve in here has genus 1/2 times n minus 1 plus 1. And of course, if we want to find If we want to find multi-sections with infinitely many rational points, we hope to find low genus curves. And so by playing around with curves in this system, we hope to get still high enough dimension to find curves, and but bring the genus down. And one system where we looked was minus 3kx. This has dimension 6, and a general curve here has arithmetic genus 4. And we started looking in this linear system where this is a bit abusive notation, but here we mean all the curves in minus 3kx that are singular in the point R. So this point R that we start with. And because of this singularity, the genus drops already by 1. And the dimension of this system, so all the curves that are also singular in R, is 3. And then we try to look for curves in there with 2 more singularities. So in general, the curves there had genus 3 because of this singularity. But if they would have 2 more singularities, they would get genus 1 or even lower. So that is how we started looking for this. And this curve just came out of the generators for this system. And it turned out to have multiple singularities like we needed. So this curve comes with an automorphism, sigma, sending a w to zeta3 squared w, where zeta3 is a primitive root of unity and a primitive cubic root of unity. And CR is a 3-section, and it's singular in R, sigma R, and sigma square R. So it has this very nice symmetry by sigma, where we don't just have the singular point R that we imposed ourselves, but we get 2 other singular points kind of for free. They just happen to be there as well. So this is a drawing of the 3-section. It is singular in R, but also in sigma R and sigma square R. And sigma sends a point always to another fiber because it acts on W. Okay, and the main proposition or an important proposition about these 3 sections is that if R is not contained in the pullback of an exceptional curve on the Del Pezzo surface, base chain to the algebraic closure, then this 3-section either contains a section that is defined over K, or it is geometrically integral and has geometric genus at most 1, in which case R, sigma R, and sigma square are all double points. So that is actually the case I drew here. Okay, so there's a lot in this proposition, but first let's look at the first part. So if it's contained in the pullback of an exceptional curve on X base change to the algebraic closure, well, these pullbacks of these exceptional curves, they are actually sections of this elliptic surface. And I said before, there's 240 of these exceptional curves. So these are 240 sections of my surface. So if I look at one fiber, there are at most 240 points on that fiber that are contained in the pullback of an exceptional curve because they're all sections. So just by eliminating this, or just by realizing that this only happens to 240 points on one fiber, we get the following corollary from the fact that we assume that there is a point on our surface which is non-torsion on F on this fiber. Because this point is non-torsion on this fiber, we have infinitely many rational points on this fiber. And therefore there's infinitely many multiples of this point, such that the 3-section either contains a section defined over K or has genus at most 1. So I just eliminate one condition, one result from the previous proposition. So you should think of this fiber of the point where we start with. So we have this point P that we assume is on my Del Pezzo surface. And on this fiber of P, there's infinitely many points R for which I have such a curve, a 3-section, and it either contains a section over K or it has genus at most 1. And here I drew 2 of them. Yeah, but there's infinitely many. Okay, so let's go case by case now. If there is such an R such that the 3-section contains a section over K, well, the Mordell-Weil group of this elliptic surface is torsion-free. This is true because we work with an elliptic surface coming from the Del Pezzo surface. So this section has infinite order. So there's infinitely many multiples of this section on my elliptic surface, and they all have infinitely many rational points because this section was defined over K. Therefore, the set of rational points on the elliptic surface is dense. So in the first case, if there is an R on the fiber such that I have a 3-section that contains a section, then the rational points on the elliptic surface are dense. So we are done because this implies the density of the rational points on the Del Pezzo surface. Okay, in the second case, if there is an R such that this 3-section has geometric genus 0, well then this 3-section has infinitely many K rational points, because we always have this unique third point of intersection on the fiber. So it is a curve of genus 0 with a rational point. And therefore it has infinitely many rational points. And now we can base change my elliptic surface to this curve, and then we have actually a section on this elliptic surface, and this section has infinite order, and it has infinitely many rational points. So the rational points on this base change elliptic surface are dense, and therefore also the rational points on this elliptic surface are dense, which of course implies again the density of the rational points on the Del Pezzo surface. So the first two cases of this corollary, if CR contains a section or CR has genus 0, those will imply the density of rational points on my Del Pezzo surface. So what if none of these occur? Well, the corollary says that there's infinitely many multiples for which one of these things has to occur. So then it means that there's still infinitely many points on the fiber, such that this 3-section has geometric genus 1. And now we have a whole open set on my fiber of these points, and we call this set F0. So for every point in F0, there is so F is the fiber of the point P we started with, and for every point in F0, there is a 3-section which is geometrically integral of genus 1. So here I drew again the picture you saw before. So for every point in this F0, I have this genus 1 3-section. So if I take the normalization, I get a smooth genus 1 curve. And I have a point on this smooth genus 1 curve because as I showed you before, this is how the 3-section looks. It has 3 singular points. And on the fiber we started with, it has a unique third point because it intersects every fiber with multiplicity 3. So I have a smooth genus 1 curve with a rational point, and therefore I get an elliptic curve. So the normalization of this 3-section gives an elliptic curve for every point in this open subset of my fiber. But I also have another point on this elliptic curve, which is the sum of these 2 points. So sigma can also, of course, act on Q, and then I get sigma Q and sigma square Q. And since the sum of Q, sigma Q, and sigma square Q is defined over K, and Q is defined over K, this sum is also defined over K. So for every point in this open subset of my fiber, I get an elliptic curve with already a point on it. Okay, we can also do this for the generic point of the fiber. So let eta be the generic point of the fiber over the function field of the fiber. Then we can, just as before, construct this 3-section. Now it's of course a 3-section of the elliptic surface base changed with the function field of the fiber. Yeah, it's a 3-section of this elliptic surface. And it also has this elliptic curve corresponding to it, where I take the normalization, the normalization of this 3-section, and I have this unique other point Q, and I have another point d eta. So everything I did here, I can also do for the generic point of the fiber by base changing to the function field. And another key proposition in this whole proof is that this point on this elliptic curve is non-torsion. Yeah, and this we showed by just studying the division polynomials of this elliptic curve and using the recursion formula to show that they will never vanish. Okay, so here's a schematic drawing again. So this is my fiber. I have a generic point and there's this elliptic curve lying over it. And for every point in the F0 set of the fiber, I have this elliptic curve. And this elliptic curve, we found a Weierstrass equation for it with magma. And this gives rise to a whole elliptic surface of over this fiber. And we showed that this elliptic surface above these points exactly gives the elliptic curves that we started with. So we now have a whole elliptic fibration on my fiber that I started with. So the fiber of the point P. So you have the elliptic surface over the Del Pezzo surface, and over one of those fibers, you have another elliptic fibration now. And this elliptic fibration has a section of infinite order. This is the point Q that acts as the 0 point of every elliptic curve. But we had this point D, or D eta, I called it before, and we showed that this is non-torsion. So I now have a section of infinite order on this elliptic fibration. So this elliptic surface over the fiber contains a section of infinite order, and therefore the rational points on this elliptic surface are dense. But infinitely many of these fibers, infinitely many of these fibers are actually birationally equivalent to these 3 sections coming from these points. And these 3 sections live in my elliptic surface that I started with. So infinitely many of these fibers are birationally equivalent to 3 sections of E. So this surface maps dominantly to E, and therefore also the set of rational points on E is dense. So let's recap what we were doing. I had this corollary that there were infinitely many multiples of the point I started with on its fiber, such that the 3 section coming from this point either contains a section defined over K, or it has genus at most 1. And we said already that if there's an R such that CR contains a section, we were done. If there was an R such that CR has geometric genus 0, we were done. And now I showed that if none of the above occurs, then there are infinitely many of these points such that CR is geometric genus 1. And we can create this whole elliptic fibration on the fiber. And we also are done. So the set of rational points is dense again. Okay, so we showed that if X contains a point as in the theorem, the set of rational points of XK is dense. And that is, of course, the main part of our theorem. And conversely, if K is finitely generated over Q, and if the set of XK is dense in X, then X has to contain a point with infinite order on the fiber. Otherwise, all the rational points would be contained in the torsion locus of this elliptic surface. And this is a closed subset. For which we use a generalization of Morel. So you can bound the order of torsion on these fibers, and this generalization was shown to us by Colliotelin. So this proves the converse of the converse statement of the theorem. Okay, and then I want to finish by an example. So if we now have the Del Pezzo surface of degree 1 given by this particular equation, then we take the elliptic surface obtained by blowing up the base, point O. And here we can very quickly check with magma that this fiber above the 0.11 is smooth and has rank 2 over Q. So in this case, the Del Pezzo surface contains a point that lies on a smooth fiber and has infinite order because there is a smooth fiber with positive rank. And therefore the set of Q rational points is dense in X. We can also compute this explicitly. So we have 2 generators for this fiber, these 2 points, P1 and P2, and this we also found with magma. And we can create these 3 sections of the elliptic surface for each of these points. So for example, the curve, the 3 section related to P1 is cut out from the surface by this equation. And we can create this elliptic curve, which has this Weierstrass equation. And the point dP1, which is the point that we want to check for non-torsion, has this psi coordinate. And by Nagel-Lutz, this implies that this has this is non-torsion on this elliptic curve. So in many cases, you can actually find explicitly one of these 3 sections of the surface and actually show that this has positive rank. And then you find, infinitely many rational points on this 3 section. Okay, that was all I had to say. It's a bit early, I'm sorry, but thank you for your attention.
Okay, well, thank you very much. I think that's a talk that would have